Happy Thursday. Another week. Spent the last 2 days looking at volumes. We're going to spend today looking at 2 other measures. All right, so you're familiar with distance, right? Distance between points. So basically, what's the length of a straight line? But what if you don't travel a straight line? And it's just some arbitrary curve, and I ask for the distance, the length of the curve. That is arc length. We're going to look at that today, and we're also going to look at surface area. And so if you take a curve, rotate the curve about an axis, you get a surface. We're going to now calculate the area of that surface. Right, 2 formulas for arc length. Integral a to b of the square root 1 plus dy dx squared dx. Right, so that is if our curve is written as a function of x. Not difficult to show that if instead we have a function of y, we just switch the roles of x and y. By the nature of the beast, these integrals are not pleasant. In fact, most of the time, for most curves, you're probably going to have to use a numerical technique to integrate. I believe most of the ones we're going to look at work out nicely. All right, so we'll take a look at this curve here, 3y to the 3 halves minus 1. We want the length of that curve over the interval 0 to 4. So arc length. Integral 0 to 4. Square root 1 plus, what is the derivative of x with respect to y? What was it? Right, so square root 1 plus 9 halves y to the half, all squared, dy.
Technically, it's the integral of the x equals 3y out of 3 half. Is that Is it for whichever in here? It's technically the x equals 3y real 2.
Well, that's dx dy, this part here, right?
Yeah.
So you take the derivative and then you square it. I do not. Square root 1 plus 81 over 4y. You should be able to see this is going to be a u sub. Right, what's the derivative of what's under the radical? So we're going to need an 81 over 4 dy, which we do not have. So we're just going to have to multiply the result by 4 over 81. All right, now it's just the integral of the square root of u. All right, 2/3 u to the 3/2. And this will be 0 to 4. Oh joy. 81 times 3. What is it? 243. When y is 4, we're going to get 1 plus 81 to the 3/2. So that's 82 to the 3/2. I'm going to write it this way for right now. Minus now when y is 0, it's just 1 to the 3/2. (82 to the 3/2) is not 28. Hmm?
Williams.
Shouldn't be 123. Because 82, square root of 82 is not rational.
7.
Right. If you go approximately, it's about 742.5, but that's not what we want. We want exact answers. So it'd be 82 square root of 82, and I don't think root 82 can be simplified, can it? 82 is what? 2 and 41, and 41 is prime. So it's just 82 root 82. Oh, this one's tough. What's 1 to the 3/2? 1. Whew. There's your arc length.
Just leave it like that.
Yep. Unless I ask for an approximation. So that's what I mean. I mean, these integrals are not going to be nice. And if you really wanted to, I guess you could distribute that 8 over 243 through, but I don't really see the benefit of doing that. Find the length of the curve. 24xy is equal to x to the fourth plus 48 from x equals 2 to x equals 4. So here we go. An implicitly defined curve, which most curves will be implicitly defined. At least the more interesting ones will be. But we're going to need either a function of x or a function of y. Well, they tell us which one to do. They give us an interval for x, right? So we might as well write this as y equals a function of x. That is simple to do, thankfully. Just divide everything by 24x. That'll be x cubed over 24 plus 2 over x. The arc length will be the integral from 2 to 4, square root of 1, plus the derivative of that squared. So what is y prime?
Here for 24 x squared plus 2 ln.
First term you can simplify. Second term you did an antiderivative. Right, the second term will be minus 2 over x, not 2 over x. 2 over x squared. Right, the derivative squared. So you take the derivative and then you square that. Let's do some algebra. What's the formula? Of course, you'd be able to do to any positive integer, right? Because we looked at that in Calc 1. But yes, this is the formula if you take a binomial and square it. Remember that? So we're gonna apply that. X to the fourth over 64 minus twice the product. So x squared over 8 times 2 over x squared. It's a quarter. Double it.
Negative product since the second term.
Technically, it's x squared over 8 times negative 2 over x squared. Right? But because I know that, I'm just going to do minus, and then I'll just look at their positive product. Right? Because technically, the formula I should have written down was this one, right? And the thing that changes is that middle term becomes minus. But that's exactly why, because that second term is negative, so it's actually like a positive times a negative. Two over x squared squared. One minus a half is a half. But isn't that a perfect square? Isn't that x squared over 8 plus 2 over x squared all squared? The interval here doesn't really matter yet. If you look at x squared over 8 plus 2 over x squared, that will never be negative. Right? Because the x's are being squared, and then you're adding them. Which means we don't need to worry about absolute values, because it's always positive. Oh, well, now that integral doesn't look so terrible. What is the antiderivative of x squared over 8? Yeah, you did derivative. What about 2 over x squared? What is it? Minus 2 over x. By the way, you could have made it easier. The derivative of x cubed over 24 plus 2 over x was x squared over 8 minus 2 over x squared. Power rule. Add 1 to the power and then divide by that power. The power is minus 2. Right. Or you could just look at this and go, okay, so this was the derivative of x cubed over 24 plus 2 over x, right? Only difference is it's now plus instead of minus. So the antiderivative would be the same function, except you switch the plus and with the minus. Because that's what an antiderivative is, right? It's the opposite of a derivative.
That always hold true.
No. It worked out nicely for this one because of how this bit worked out. Right, when you squared it out and then simplified, it wound up being the exact same square except the sign changed. That usually doesn't happen. Right, but of course, when math people write books and resources and problems, they tend to pick the functions that work really, really nicely, which is not the vast majority of them. But if you ever see something like this, where it works out that nicely, then that's probably what's going to wind up happening. Right, that from 2 to 4. Four cubed. Oh, without even doing 4 cubed. 4 cubed over 24 is going to be what? 4 squared over 6? So that's 36 over 6, which is, I'm sorry, 16 over 6. 4 squares is 36. 16 over 6, which is what, 8 over 3? Two cubed over 24. Well, that's just going to be easy to do. That's 8 over 24, which is a third. Then minus 2 over 4. Plus 2 over 2. Seven thirds minus a half plus 1. Common denominator is 6. That's going to be what? 14 minus 3 is 11. Plus 6 is 17. Arc length is 17 over 6. Okay. So the curve we're going to look at next is a curve you see every single day. Catenary curve. But I guarantee you know what it is. Right, you have two poles and the power line
Oh,
between them.
Oh, yeah, now it's
That's a catenary curve. That's what it's called. So it's represented with this function, right? Arbitrary a, so a can be any number. Now, this is actually not the most convenient way to represent it. Catenary curve is most easily represented using a hyperbolic function. In this case, it is a hyperbolic cosine. So I believe I'm trying to, yeah, be that. Which would make this problem a lot easier, but we didn't study hyperbolic functions. So we're going to use the actual definition of the hyperbolic cosine as hyperbolic cosine of x is equal to e to the x plus e to the negative x all over 2. All right, so we're going to go ahead and calculate the length from 0 to a. Right, so basically what we're doing is imagine that's your pole, right? We're going to calculate the length if this arbitrary distance is a, and then we go to use that to go, okay, well, now what if we move the pole? Right, what's going to happen to that length? Assuming that we can infinitely extend the power line. Right, it's not, that power line's not already a fixed length. Integral from 0 to a, square root of 1 plus the derivative of our function. Well, that a over 2 is a constant, so that can come out. So what's the derivative of e to the x over a plus e to the negative x over a? And so that's the first term. You forgot chain rule.
Yeah, I was not thinking of a as a constant, even though you just said it. So my mistake.
Ooh, that would actually be really hideous if a was not a constant. Then we'd be in Calc 3 territory.
Yeah, I don't know why. But the I, is that an I in the look?
Where?
So ours is still bad. I thought that that slash, the division symbol was an I.
Oh, no. Well, that again, that would then put us into complex analysis.
I just thought you were really mean. Sorry.
That would be a senior level math course. I mean, I could give you guys a complex analysis exam if you want.
That's all right.
Actually, they're easier than this stuff.
Thanks.
No, it actually is. If you integrate integrating a complex valued function is a lot easier than integrating real valued functions, which is odd, but it is because of the theorems of complex analysis. Notice a 1 over a common. That's going to drop out of this a. gonna be a 1/2 squared, which is a quarter. Now square out e to the x over a minus e to the negative x over a. So it'll be the first term squared. E to the 2x over a. Minus twice their product. What is e to the x over a times e to the negative x over a? I know what you did, wrong property. Multiply same base. What do you do to the exponents? It's just 1. Oh, right, but then you have to double it. So it's -2. Then plus second term squared. Yes, this is another one that's going to work out very nicely. I'm going to factor out a 1/2. So I'm factoring out a 1/4 from what's under the radical. Square root of a quarter is a half. That's just to get rid of fractions. Now you factor a quarter out from 1, you're left with 4. Now look at what's under that square root. That's a perfect square. Once again, e to the x over a plus e to the negative x over a will never be negative. It will also never be 0. Because no matter what you raise e to, you're never going to get negative. E to the x over a times e to the negative x over a. Add the exponents, right? So what happens when you add the 2 exponents? So you're left with what? What's e to the 0? Another way you could look at it is, because that's a negative, that's e to the x over a divided by e to the x over a, which is 1.
Yeah.
Because that's technically a negative e to the negative x over a. Right, so that's why that has to be negative. That means we don't need absolute values, and we can just write this now as half the integral 0 to a, e to the x over a plus e to the minus x over a dx. U sub. Let u be x over a. Then what's du? It's 1 over a, right? Again, look at the original function. The only thing that changed, this is a plus, whereas the original derivative was a negative. So the sign in the original function is also going to just change. Now we just evaluate that. Okay, good, that still works. Now we just evaluate that from 0 to a. We're going to get e to the a over a, which is just 1. Right, so it's just e to the first power, minus e to the 0, which is 1, minus e to the minus 1, plus e to the 0. Left with a over 2. I don't know why I did a plus. A over 2 times e minus e inverse. If you want to write as a single fraction, e squared minus 1 over e. If you want to distribute the a over 2 through. This is the length of a catenary curve where the distance between the poles, let's call them, is a. That is a known length formula.
That useful.
Just to find the length of catenary curves.
In like applications wise, that's something architects use, construction.
Possible. I don't study applications in terms of architecture and stuff. My main field of applications would be physics.
Instead, we see them everywhere though.
Yeah. But not in physics, right? It's not really used in physics. And of course, now as a mathematician, my answer is who cares what it's used for? It's just there. It's interesting. Oh, excellent. Okay, we're off of arc length. We're now on the surface area. Again, you have two formulas for surface area. That's if you're rotating it about the x-axis. And if you're rotating it about the y-axis. And generally speaking, these integrals are not nice. They're even worse, generally speaking, than an arc length. For some reason I didn't say about what axis, so supposed to be about the x-axis. Now, we actually go ahead and look at this. Y squared equals 12x. There's our curve. Right. Here's the portion we're looking at. It's that red segment that we're rotating about the x-axis. Well, if we just take half of this and rotate about the x-axis, don't we get the exact same surface? That means we actually need half of this plot to get the same surface. So without loss of generality, we're just going to take the upper portion. All right, that's the portion in quadrant 1. So write y squared equals 12x as a function of x in the first quadrant. So what does y equal? There's your function. That's what's going to be rotated about the x-axis from 0 to 3. Surface area 2 pi integral from 0 to 3 of y times the square root of 1 plus the derivative of y, all squared. What is the derivative of y? That. How did you get that? But is it 12? It'd be root 12 over 2 root x, which I'm going to write as 6 over the square root of 12x. And dx. Six over root 12x all squared would be 36 over 12x. Just 3 over x, right? That square root of 12 is a constant. So why not write square root of 12x as square root of 12 times square root of x, and then pull out the root 12. But by the way, root 12 can be simplified. It's 2 root 3. I have a 4 pi root 3 times the integral from 0 to 3. I'm also going to distribute that root x through. Right? Because remember, if you have the square root of a times square root of b, it's the square root of a times b. So the integrand just becomes root x plus 3. X plus 3 has a derivative of 1, which makes u sub very simple. Two-thirds times x plus 3 to the 3 halves. Is your antiderivative. I don't like that 8 pi root 3 over 3. I'm gonna write that as 8 pi over root 3. It's contrary to what you were told in algebra, you are allowed to have square roots in the denominator. Go away, thank you. Evaluate at 3, we get 6 to the 3 halves. Evaluated at 0, we get 3 to the 3 halves. Six to the 3 halves. Six root 6. 3 to the 3 halves. 3 root 3. That can be simplified. Factor out a 3 root 3. Oh, I factored out a 3. I don't know why I wrote that as a 6. 24 pi times root 2, 2 root 2 minus 1. That is our surface area. Right, what's 3 over root 3? Oh, I'm sorry. It was root 3 over 3. 1 over root 3. Right, because it's 3 to the 1 half over 3 to the 1, which would be 3 to the minus half. So I just simplified the root 3 over 3. Those?
Yeah.
This one. Okay. This one's kind of fun. Yeah, I didn't. This one's being rotated about the y-axis. That means we need this written as a function of y. I don't think this is the one I was thinking of originally. It's not. So we're integrating. Oops, I forgot the 2 pi. I always do that. 2 pi times the integral 1 to 3 of x this way, just so I don't have to write parentheses. Times the square root of 1 plus now dx dy squared. So we want the derivative of this. Or you could do the derivative of this one, doesn't matter. And that gets squared. I think before I square that, I'm going to combine that into a single fraction. Be what? 1 minus 2y squared all over 2y, and then that gets squared. All right, we're going to get 1 minus 4y squared plus 4y to the 4th all over 4y squared. just looked at my work and I'm wasting my time. Oh well. Algebra never killed anyone. Common denominator 4y squared, right? 4y squared minus 4y squared, they're gone. In the numerator, we're left with 1 minus 4y to the fourth all over 4y squared.
Why would it be minus 4y squared?
Should be plus, shouldn't it? Square root of 4y squared is 2y. Multiplied by 4, that's where that 8y comes from. What happened now? Okay, did I screw up here or here? Move it on there, 2y. Oh, I screwed up here. That should not have been a 2y squared. Should have just been a minus y squared. I already had the 2 in the denominator. Wait, what? What's going on? Why did this erase? That was minus. Which makes this 2. Just going to change what this is. 4y squared, yeah, that's a 2y. Okay, 1 plus 2y squared plus 4y to the fourth. Okay, that's going to make this right. I have oh right, this is no longer 4, is it? That's now y to the fourth. Why is it erasing up there too? Something weird's going on. Read it. Y to the fourth, which makes that y squared squared. Perfect. Not wasting my time. All right, 1 plus y squared would never be negative. Factor out that 1/8. distribute the numerator through, we get 2 log y plus 2y squared log of y minus y squared minus y to the 4th. All that over y. I just put that 1 over y through to every single term in the numerator. Those 3 are simple antiderivatives. That y log of y, though, that is going to require integration by parts. Oh, that sucks. Actually fairly certain, though, that that is 1 in the table. Big exponential logarithmic. U to the n log of u. Yes, it's number 47 in the table. Perfect. Right. Antiderivative 2 log y over y. U sub, let u be log of y. What's du? 1 over y, right? This is just the integral of 2u. Which is u squared, so it's log squared of y. Number 47 tells me that y log of y is going to be y squared over 4 times 2 log of y minus 1. And then, of course, those other 2. Log squared y from 3 to 1. You get log squared of 3 minus log squared of 1. What's log of 1? 0. So we don't have to worry about that term. Plus, here's the fun part. Be 9/2 times 2 log of 3 minus 1. Then minus 1/2 times -1, right? Because again, log of 1 is 0. Minus 9/2 plus 1/2 minus. Get that log of 19,683 from. I have no idea. So minus 3 to the 4th over 4. 3 to the 4th is 81. And plus a quarter. Oh, I know where I got it from now. Okay. So log squared of 3 plus 9 log of 3, right? Should be that 9 halves through. Minus 9 halves. Plus a half. Oh, look. 9 halves minus, it's another minus, right? Okay, so that's now what? 8 halves. Minus 9 halves would be negative 1 half. Plus half. Oh, that's nice. Plus a half is 0. That should not be minus 28, though, should it? Just write it out. Minus 9 halves plus a half minus 9 halves plus a half. Yeah, I did that wrong. That's negative 18 over 2, which is negative 9. Plus 1 is minus 8. Yep, okay. Minus 8, and then that is minus 20. Right, negative 81 over 4 plus a quarter. And minus 28. There's the surface area. I only had to cheat once because I didn't want to do integration by parts. This one. That's the one I was thinking of. Well, it's also going to depend on that. I think it is. So I'm just going to do this. One to 20. I'll just change it by 1 each time. All right, so let's see what happens as A increases from 1 to 20. I'm just considering integers. Uh-oh. That's not supposed to happen. Oh dear. Oh, that's why. It's going too fast. Needs time to actually load it up. And I actually didn't need to. Good, I can actually set Y just to go -1 to 1, it looks like. That. Look what's happening. Same shape, right? But what's happening as A increases? This is changing, isn't it? And yeah, this is going to get higher, so I'm going to have to adjust my A. Let's do -10 to 10. It's fine, I don't care. What was I? It was up to 6. Right? So we get the idea. We just want to rotate one loop about the x-axis. So we can choose either the left or the right. Let's just choose the right loop. But again, if we rotate the entire right loop about the x-axis, it'll be the same thing as just rotating that upper part about the x-axis, right? So we're going to limit this to just looking at the first quadrant. And notice it's going to go from what? It's going to go from the origin out to whatever the value of A is. So our interval is going to be 0 to A. Since we're rotating about the x-axis, we need to write this as a function of x. So y equals there's our function y. Wait. We're gonna have to take that derivative. Which we don't have the time for. Actually, before I do that, I'm going to define y of x. It'll be easier that way. Said as well as the square root of a squared times x squared minus x to the fourth, and it was all over 8a squared, right? Two pi integrate y of x times square root 1 plus y prime of x squared. X goes from 0 to a. Uh-oh. Uh-oh. Taking a while. Oh, this is not good. Oh, this is really not good. Oh dear.
When you code that, you have to say what you were deriving or integrating with respect to.
I did.
Oh,
Right, so this first is saying it's with respect to what, and then from what to what. Okay, perfect. As long as the real part of a is greater than 0, which we're assuming it is. We're assuming it's a real number. And imaginary part of a is equal to 0. Again, we're assuming it is. Then it's 1/4 pi a squared. So this condition is satisfied. We're assuming a is some real number. Furthermore, we're going to assume that a is positive. That's why it was taking a while. Which is what I got with a bunch of algebra, which sadly I just don't have the time to go over all that.
so by default, if they don't tell you like the boundaries, you would do 0 there.
Now that came from our analysis of the graph. Right, one loop. Right, we said if we're just going to do the top, that goes from 0 out to whatever a happens to be, right? Because if you keep moving this, you see that that's going to keep extending out to whatever a happens to be. So that's why it was 0 to a. Those integrals are not going to be nice integrals typically. Technology is going to be your best friend here. Questions? Arc length and surface area. We will be revisiting arc length and surface area when we study parametric equations. And that'll be revisited again in, I don't know about surface area, but arc length will be revisited again in Calc 3. Actually, surface area will be too, but that's a different formula.
Yep. So I'll just